So I'll share my screen. Yeah, so am I audible?
Yes, sir.
And the screen is visible, right?
Yes, sir.
Cool. So as always, quick introductions. So this course is analog IC design. It's an NPTEL course, and the instructor for this course is Dr. Shankar Aniruddhan from IIT Madras. My name is Mayank Anupam. I hold these tutorial sessions. I'm also a PMR scholar and a PhD student at IIT Kanpur in the Department of Electrical Engineering. Fine, so let's quickly proceed with the questions. So, before that, any doubt in the previous week's assignment?
Yes, sir.
Yeah, so come on,
I
ask me.
think yes.
So, I do not have. Yeah, yeah, you tell me what is the doubt. Hello? Hello?
Hello, sir.
Yeah, yeah,
Yes, sir.
yeah, yeah,
I have one doubt, sir.
yeah, yeah, go on.
Sir, the capacitance at that node, sir, M naught of the capacitor will not affect that.
Okay,
Will
let's.
not.
Okay, okay, 1 second. So, let's put a page here. Session. Fine. And let's 1 second. Okay, 1 second. 1 second. 1 second. Yeah. So yeah. So what were you asking?
At node M naught, sir, the capacitance will be not affect the pole and the zeros because it is virtual ground in differential mode. Am I correct, sir?
The capacitance at M naught. You're saying where is M naught?
Yes, sir. Uh, that is tail current source. Tail current source in
In which
op amp,
assignment?
sir.
Which assignment are you saying? Are you talking about?
Not assignments, sir. General, sir. In op amp, sir. Op amp, there will be trail current M naught, no, sir.
Yeah, correct. There will be yes.
that will be in virtual ground in differential mode. So even if the capacitor is present, it will not affect the pole or zero of the total op amp.
Yeah, correct. If it is it will not affect if it is fully differential op amp, and it will not affect only in the differential case. In the common mode case, it will affect. Is that clear?
Okay,
Yes,
sir.
sir. In common mode, if resistor is present, then it cannot be zero, no, sir, that voltage.
No, no,
Common
it
mode.
cannot be zero in that case. No.
Sir, my question is, that eighth question is there, no, sir? Assume the tile current source requires a DC voltage of 100 millivolts across it works properly. Determine the minimum input common
Okay,
voltage for
one
the
second.
op
One
amp.
second.
Yes.
What's this? Yeah. So what was the question?
Yes, sir. Question number eight, sir.
What was question number 8?
Just a minute, sir.
Yeah, yeah.
Assume that tile current source requires a DC voltage of 100 millivolts across it to work properly.
Okay.
Determine the minimum allowed input common mode DC voltage for the op amp to work properly. All devices are to be in saturation region.
Yeah.
Yeah, this
Fine.
is the condition.
So what is the problem in that question? So what were you trying to do? So this is the situation, right? Let me draw a
Yes.
little bit. The situation is so this is question 8, right? The situation is that you have this MOS op amp. You have this op amp here, and this is the input, and you have this tail current source here. You have a tail current source here, okay? And this is VID. This is okay. This VID is between these two terminals. Fine. And this is shorted like this. This is a diode connection. This is V out. Fine. And cool. So what is the issue? See, they have already mentioned that you require certain amount of voltage. So let's not call this VID. Let's call this VIP. Let's call this VIM. Okay. Now they have already mentioned that you require certain minimum amount of voltage here, right? Let's call
Yes,
it
sir. 100 millivolts.
it's 100 millivolt, right? Correct.
Yes, sir.
Yeah. So now tell me what should be the minimum common mode voltage at this input. That is the question, right? That is the
Yes, sir.
question.
Yes, sir. Exactly. Yes, sir.
So now
Exactly.
tell me what should I do? I mean, why is the question asked in that manner? Why have they asked minimum at this point?
Minimum means if it didn't mean that voltage that MOSFETs will get into a triode region, sir.
Which MOSFET will get into triode region?
I think M1 or M1, sir. I think.
If this starts going down, which MOSFET is going to go into triode region?
Okay.
I mean, you understand what is the meaning of this question? They have asked you what is the minimum possible common mode at this input. So for common mode, what do you mean by common mode inputs? It means both the inputs are same, right? Both the inputs
Yes,
are
sir.
same. That means at both the places you are applying the same input. This is VCM. This is also VCM, right? So
Yes,
they are
sir.
asking what is the minimum possible value of VCM so that all the transistors remain in saturation. So tell me, if VCM starts to go down, Which transistor will be affected first?
M0, sir.
Why?
I mean, there is a relation, sir.
No, no. How
Uh,
come? I'm asking why. Why should it be affected first?
yes, sir. Sir, VGS will get VCM is getting decreased.
VCM is
Then
decreasing,
VGS
yes.
will, yes, sir. VGS will get affected, no, sir.
Uh, which VGS? This VGS or this VGS?
M2, sir. Yeah, both, sir. VCM is getting decreased.
So VCM is getting decreased. So which VGS are you talking about? That's what now. So are you talking about VGS of M1, M2, or are you talking about VGS of M0?
M1, sir. If VCM is decreasing, no, so that gate voltage is get decreasing, right?
This gate voltage decreasing. So this and this, right? So
Yes,
this, you are
yes,
saying
sir.
that this is these two VGS are decreasing. You are saying, or decreasing. What are
Ye-
they doing?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yeah, yeah. So what are they
That
doing? Are they decreasing, increasing? What?
they are they will be decreasing, sir.
Why?
The
Why?
gate
Why?
voltage.
Why? That's what. Now, why should they decrease? Who sets the
The,
VGS of these transistors? What sets the VGS of these two transistors?
means that gate and source voltages are relations, sir. With that relation, it will
Yeah. So
they
what
may
is the
decrease.
relation? I mean, who governs the relation? What quantity governs the relation here?
Sir, current, sir.
I know current.
Correct.
Yeah.
Yes. So the current. So okay, let's. The current here is I naught, right? Right now. The current here is I naught, correct? Now this I
Yes,
naught
sir.
is supposed to divide equally in between these two, right? I
I
naught
know
by
better.
2,
I
I
know.
naught by 2, right? Now,
Yes, sir.
if you now the current in this I naught by 2, it is fixed, right? It cannot change. It is fixed by these two transistors, isn't it?
Yes, sir. Because current mirror. Yes,
Because
correct.
they are current mirrors. Yes. Now,
Hmm.
if you somehow start decreasing VCM, okay. No, before that, for this current to flow, for this current I naught by 2 to flow between these two transistors, right? You have to have certain amount of VGS, right? In M1 and M2, you need to have, right?
Huh.
And how will you find out what is the VGS of M1 and M2 for this current to flow, I naught by 2 to flow?
Root over 2 I naught by mu n C naught h W by L plus
Yeah, so
Vt.
you will use this relation, right? I naught by 2 should be equal to uh, mu n C ox W over L and divided by 2,
VGS minus.
assuming everything is in saturation, v
Yes.
VGS of M1 M2 minus VTH, right, the whole square, and you assume that there is no channel length foundation at this point. Okay, I'm assuming that. So from here you can calculate, right, what is the VGS required. So what is the VGS required?
Yeah. I not by mu1
I
square
naught by
square
mu
W
n C ox W over L
W by square root of plus VTH, sir.
square root plus VTH, right?
Yes, sir.
Correct. Now tell me if this VGS, what is this VGS? Let's call this voltage. Let's call this voltage as Vx. Okay, I'll call this voltage as Vx. Okay. Then what is VGS of M1 and M2? What is VGS
VCM
of
minus
M1 and
Vx.
M2? Yeah. Someone was saying something.
VCM minus VX.
Correct. It is VCM
Yeah,
minus
man.
Vx, right? And that is equal to what? This guy, I naught by mu n C ox W over L and plus VTH, right? So from here you can see that uh, yeah, so from here you can see that this VGS is clearly not dependent upon VCM, right? VGS is simply a function of I naught, isn't it? If the
Yes,
current
sir.
is changing somehow, only then can VGS be affected. Otherwise, if VCM is changing here, VGS is not going to be affected, right? So, what is going to be affected in that case? If VCM is going down, Vx also has to go down, isn't it? But you can also clearly see this, that Vx is equal to VCM minus I naught over mu n Cox W over L uh, plus VTH. This goes inside the brackets, right? So if VCM goes down, Vx also has to go down, isn't it?
Yes, sir.
Right? Now what happens if Vx starts to go down?
M naught will
MCO
come out
will
of
be
saturation.
tried region.
This guy starts to go down. This terminal is fixed. I mean the gate of M0 is fixed, right? But its drain voltage is going down. So it is definitely going towards linear region, isn't it? Triode region,
Yes. Yes,
right
sir.
now.
Yes, sir.
So in that case, that is why they have asked you what is the minimum possible VCM that you can use in order to make sure that while making sure that M0 is not going out of saturation. So you know that already, you already know that the minimum that Vx can go is how much? 100 millivolt, isn't it?
Yes, sir.
That is
100
already
millivolts.
given. So you can use this like Vx minimum is equal to 100 millivolts, correct? Definitely Vx is greater than equal to, has to be greater than equal to Vx minimum, isn't it? Which is equal to 100 millivolts. So what is Vx from here? Is equal to Vcm minus I naught over mu n Cox W over
Plus
L
VTH.
plus, sorry, minus VTH, right? And this has to be greater than equal to Vx
100 mil.
minimum, which is equal to 100 millivolts, right? From here you can work it out. So VCM, you will get some minimum value of VCM, which is equal to 100 plus VTH plus root over I naught over mu n Cox W over L, right?
Yes, sir.
So understood, right?
Yes, sir. Perfect, sir.
Yeah. And now tell me what should be the maximum possible value of VCM? So how will you do that? First of all, will there be a maximum possible value of VCM? I mean, if you keep on increasing VCM, is there a possibility that some transistor will go out of saturation?
No, sir.
Sir, yeah.
What? Yeah, you assume that for this question, you assume that these two are sorted like this. Okay. I mean, this. Let's say this is the op amp. Okay, let's say this is the op amp. Then this is plus, this is minus. You assume that this is in this manner, and these two are VCM. Now tell me, will not only this is VCM and this is not VCM. This is connected to this output, right? Now tell me, will this, if you keep increasing VCM in this case, something will happen or not?
Yes, sir. Definitely, sir.
What will happen?
And that, I think. Sorry, M3. M3 on 4.
Yeah, come on.
M1 will move into triode region, sir.
M1 you are saying? This transistor M1?
Yes, sir.
Are you sure?
Yes, sir. As
Yeah,
VGS
so
increases,
that's what now. You have to see which transistor have the possibility of going out of saturation. So there is when you keep increasing VCM, this guy is fixed, right? This voltage will be fixed always because this is being fixed by the current that is flowing here, isn't it? The current that is flowing here is fixing this voltage, uh, which is the voltage across M3, isn't it? Hello, are you there?
yes, sir.
Yeah.
Yes, sir.
Yes, sir.
Correct. Now, if this voltage is fixed, this voltage is fixed here, and you are increasing VCM, that means you are reducing the, I mean, you are basically what? You are increasing gate of M1 and keeping the drain fixed. So definitely M1 has the possibility of going out of saturation, right?
Yes, sir.
Yes, yes, sir.
Similarly, you are increasing VCM, so definitely gate and drain of these two are moving, isn't it? Moving up. Fine. Fine now.
Yes, sir. Yes.
Yeah, but the gate voltage of this M4 is fixed. The drain voltage of M4, which is the PMOS, is moving up, but the gate is fixed. So definitely M4 is also under the possibility of moving into triode region, isn't it?
Sir, in case of M1, for M1 transistor, CM VCM is increasing.
Yeah.
Then I naught by 2 is constant, right?
Correct. I naught by 2 is constant. Yes. So
Uh, so Vx also
yeah, yeah.
increasing.
Vx is also increasing. Yes. Definitely yes.
Mm. So M1 VTS should be greater than or equal to VGS minus VTH.
Yeah, yeah.
And
So that's what.
how
Na.
M1? I'm not getting how M1 will be in the triad region.
See, because
If
M1's okay. Sorry. You see M1 Vx is moving up, right? This guy is moving up. Correct. VCM is moving up. Correct. So VGS is remaining constant for M1, right?
yes, yes.
But the drain is fixed, isn't it? Drain is at the same potential always, because it is fixed by this guy here, M3. Correct? So
Yes.
drain is fixed, gate is moving up, source is moving up. So what is going to happen? Drain to source voltage is going to decrease or not,
Okay. Yeah. Yes. Yes.
right?
VTS. Yeah.
So definitely
Okay.
M1 has the possibility of going out of saturation, right?
Yes.
Similarly,
Okay.
M4 also has the same possibility of going out of saturation. So these two transistors can go out of saturation when VCM goes up. So we'll have to see which transistor goes out of saturation first, and that will decide the maximum value.
So we can show it in LT space, sir. Means how we can verify it, sir. Which transistor will go like that while keeping the values.
I didn't get your question. Come again.
No, sir. We are calculating no, sir. Which transistor will go for triode region while calculating the maximum voltage, minimum voltage. That scale range is there, no, sir.
Yeah, yeah,
Yeah, we can show it in LT space, sir.
yeah. You
Is there
can
any way?
show. Yes, you can also check with LT space. Yes, but for that
For example,
you need the models. You need model files and all.
yes, sir. If I don't maintain that voltage, if it went to triode region, is there any change will be in the AC transient analysis, sir? While showing that output to transient analysis.
I am not still getting your question. So this is the situation here.
So, hello.
Yeah,
If we consider the GDS of these transistors to not be equal to zero,
you
um,
can assume
in that
that.
scenario,
I
it
just for the purpose of illustration, I was assuming that GDS is not GDS is equal to 0.
okay. It's just a doubt. If in that scenario, does it Nagendra says that VD3 and the out should be the same if GDS is not equal to zero, but if it
What
were
is
equal to
VD3? What is VD3? This are you saying
the
this is
yeah
VD3?
that is VD3. Yeah,
Okay, and V out should be same.
same as VD3.
Yeah, yeah, that's
If
right.
GDS if it were equal to zero, would that be the case, or it's not necessary for them to be
It
the
is
same,
not
right?
necessary for them because that is what I proved last class, right? Proved in the last to last class or last class, I don't remember. This is what we
I
proved.
wasn't okay. I wasn't there. Okay, I'll just check. Okay, sir. Okay.
So this is basically when you set the biases, okay? At that time they have to be equal. I mean they will this these two voltages can be nothing but equal. They have to be equal.
But if GDS were equal to zero, then that's not the case, right? It
No,
could be
both
different,
in
right?
both the conditions it will be equal to, yeah. If GDS were equal to 0, you cannot definitely say what will be the relation between these two. Okay, that is the
Okay.
problem. If GDS is equal to 0, you cannot certainly say what will be the relation. But
Okay. Okay.
but for all practical cases, GDS is not equal to 0. So these two will have to be equal to each other. And there is no other possibility
Okay.
for
Okay.
bias
Okay, sir.
condition. Okay,
Okay.
mind it. When these two voltages are exactly same. Okay, only in that condition, these two will exactly be same.
And
There is
also,
no other possibility.
okay, so then one more thing. If we give it in the unity feedback condition, we are supplying VCM in only the non-inverting terminal, right?
This guy, yes.
Yeah. The other one is generated via
Yeah,
this
negative feedback again,
current bearer
yes.
no feedback. Okay.
Yes.
Okay, sir. Okay.
Okay. So this is a buffer, isn't it? This is a buffer. If you apply V in here, you will get V in here, right? You'll get V in here.
So, okay.
Sir, I have one doubt.
Yeah.
Sir, how do we calculate the common mode gain of this load, like with a current mirror load in the differential ampere? Like, amplifier.
What is the no?
Like how do we calculate it? Not,
You want to ask? You are asking what is the common mode gain between input and output?
yes, sir. Yes, sir.
Yeah. So what is the common mode gain? What is the definition of common mode gain?
So we apply equal incremental inputs,
Correct.
and then we
So
see how much current is flowing.
you apply VCM here, small VCM here. You apply small VCM here, and you
Yes, sir.
check what is the
Hmm.
change in V out, right?
Yes, sir.
Now so tell me what will happen.
Sir, if we apply these, then at the source of M2 and M4, the same increment will be there.
M2 source of M2 and source of M4.
No, no, not M2. The lower transistors, M1 and M2.
Okay, source of M1 and M2 are basically the same thing, right? They
Yes,
share
sir.
their sources. So yeah, so what should happen at this point here? Let's call it Vx.
So Vx will be the same increment of VCM.
Will it be? Think properly. I mean, there is R naught here, there is C naught here, there is also this I naught here. Now tell me what should happen. Yeah, so let's do this. Looks like there is an issue here. So you have this I naught here, okay? You have
Say
this
in the
as
common mode, I not
one
like.
second, one second. Let's do this. Let's first make this figure. So this is R naught, right? C naught. This is VCM. This is also VCM. You have to calculate V out over VCM, right? Now tell me what is how will you find it out? So first you have to draw the incremental picture, right?
Yes, sir.
So what should happen in the incremental picture?
The I naught will be 0.
So you are saying I naught goes to 0, right? What else?
Uh, VDD grounded.
Okay, really grounded. Fine. Anything else?
Uh,
R0 and C0 will be splitted equally for M1 and M2 set.
Are you sure? I mean, that should happen. Do you think that should happen?
so what did he say? R0.
And C0 should be split equally between the branches, the two branches.
So it is like it is not a symmetrical circuit,
Yes,
right?
yes, it is not symmetrical. You see this diode connection here. Now you cannot draw a line here, right? You cannot draw a line here and say that yeah, this and these two are exactly equal to each other. You cannot say that because this side contains a diode connection, this side doesn't have that, right? So you cannot do that here. That you cannot do. So what should happen to R0 and C0? They should simply be here, isn't it?
Yeah. Yes, sir.
So this is R0, this is C0. Now this is VCM, this is VCM, this is V out. Fine. Now
Yes,
tell
sir.
me, what should you have applied equal VCM here and here? So what should happen?
Yes.
How will you find out what
Sir,
is V out?
so since both are increasing, and say if both are increasing, then the gate source of both of the transistors are same, right? Like
Yeah, yeah, both are same.
so,
Yes, gate to
so
source.
then equal current will flow through them.
Correct, correct. I'm not
So,
saying, I'm not denying that. But you were
and
earlier saying that.
if we are increasing V in, then the source of M1 or the source of M2 should increase by the same amount, right? Because equal current has to follow.
Are you saying that Vx will be equal to VCM? Are you saying?
Yes, sir. That's what I'm
No,
saying.
that's what. No, that why should that happen? Why should I? Let's think logically. If
Hmm.
VCM is increasing, VCM is also increasing, and
Hmm.
if Vx is also equal to VCM in that case, what should happen? Well, what should happen in that case? In that case, no current should change, right, through M1 and
Ah,
M2.
ah,
If
yes,
Vx
yes.
is equal to VCM, then basically the overdrive is not changing now.
Not changing. Yes, yes, yes.
But if overdrive is not changing through M1 or M2, then current through M1 or M2 should not change, isn't it?
Ah,
But do you think that can happen? Because when Vx is equal to VCM, that means if VCM is increasing, Vx is also increasing, and Vx is the voltage across a resistor. So if Vx is changing, the current through resistor will change, right?
yes, sir.
So definitely some current is going to flow here,
Hmm.
but according to your argument, no current can flow through M2 or M1. but that is simply a contradiction, right?
Hmm.
So definitely something with Vx will not be
So
equal
we
to
can
Vcm.
write this right, like VCM minus Vx into GM1 would be equal to VCX minus Vin
You
into
have to
GM2, right?
basically you have to solve the whole circuit properly after drawing small signal and all. Okay, what there are two ways to solve this. One, you can simply do the full blown analysis. Other way
Hmm.
is that you can simply use superposition. You use VCM here and put this to
Uh,
ground. Other time, put VCM here, put this to ground, and find out individually what is the response, what is V out due to
V out
both
there.
of them, right?
Uh,
And then you find V out due to both of them, basically the combined effect of both of them by simply adding the two outputs, right?
hmm.
That you can do. Fine.
Yes, sir.
Yeah. So is that clear?
So yes, and sir, in this common mode, the R out would be different from differential mode, right? Like,
Of course. One second. One second. Yes, it will be different. Yes.
so how you are saying that it will be different, like just by looking at it?
Uh,
What is the feel for that?
okay. So one second. So first thing, for R out. One second. No, no, no. I was wrong. I was wrong. I'm sorry. For R out, it will not matter much. For R out, it will not actually matter, because for R out, you do not care which whether it is in differential mode or common mode. You all you worry about is what is the looking impedance from the output, and for that calculation you simply short both the inputs, right?
Acha, acha, yes, yes, yes,
So
yes.
it doesn't matter whether you are talking about the differential case or the or the common mode case. Okay.
So this Vx will not be at ground, right, for the common
Yeah,
mode
yeah.
case.
It
So
doesn't matter,
then
right?
that would
No, no. Even in the differential case, you cannot say that for that it will be a ground. Even in differential case, you cannot say that when you are calculating V out.
acha.
So that is only when the circuit is symmetric, right? The Vx equal to this.
Yeah, even then if the circuit is symmetric, even then it doesn't matter. When you are calculating R out from one terminal, okay. Yeah, basically when you calculate R out from one terminal, you are basically making sure that the circuit is not symmetric. Even in the fully symmetric case, when these two are basically, let's say these two are symmetric in this case also, and you want to calculate what is the output resistance here, what will you do? You will basically ground everything else. You will apply a voltage source here, right? And when you calculate what is the current. So when you do that, you can clearly see that the right half is not symmetric to the left half, isn't it?
Yes.
So definitely, yeah. So it doesn't matter whether you're talking about differential or single-ended, or differential or single-ended. It will be the same for both the cases.
So I have one more doubt, sir.
Yeah.
Like in the that differential week they taught the differential pair. So they use this V term there. So could you just briefly explain it like once more, like
What
what they're doing with it? That
we
V term they're using to make the load low, and then they're
Yeah,
using the symmetrical circuits equation.
I
So
I
terminal voltage.
I am not getting what you're asking.
So like in the video, what they did was they connected a VTERD, like a voltage source, to the V out of the differential pair with active mirror, like current mirror load.
So this is the circuit, right? You are asking the same
Yes, sir.
this circuit.
Yes, yes.
There
But
was a
in
current.
the differential mode, not in the current like common mode.
Okay, not in the common mode or fully differential. Was the circuit fully differential, or it was current mirror load?
Current mirror load.
Okay, so current mirror load here, fine, and there was a current source here, fine, and what else?
So now they have connected a VTERD, a source whose value is VTERD, to this V out.
And
And
they have connected a voltage source here. You are saying
sir, from ground to that point, V out, not from.
from ground to that point. Okay,
Yes, sir.
so like this.
And the value of this VTERD is equal to the this voltage, like uh, what is this node? So
Vout, vout.
the
minus VSG
calculated
at
load,
I naught by 2.
VDSC minus VGS I not by 2.
So I'll have to look. I mean, I'm not understanding the question. I have not seen this part. I am not understanding your question. What is the question? I didn't understand the question.
It's actually in the
Actually, in a
analysis part.
lecture, the sir was explaining that we cannot sure that Vx, that the tail point is 0.
This one.
If that, yeah, because the diet connected and the resistance are not equal or some less than M1 and M2 resistance, RTS. To make
I'll
sure the
I'll
sir added one that voltage there.
I'll have to check that. Okay, I'll have to check that. I do not know what you are asking at this point of time. I'm not understanding what you're asking, and I have to see. Okay, I'll clear
Okay.
this out in the next tutorial definitely. I've not seen this part, so I'll definitely see in the clarify. I'm not getting your question at this point, so I'll ask. I'll uh, talk about this in the next tutorial. Is that fine?
Yes, sir.
Yeah. Okay.
Sir, I
Yeah.
have one last doubt.
Yeah.
So like in a Unity buffer also,
Yeah.
how do we exactly decide which input is to be taken as minus in inverting and how which is to be taken as non-inverting input
Well,
of both the sides of the.
this is like asking after the whole Ramayana who was Ram and who was Sita. So
Sir, so I understand like this, but is there only like that logic is that we are taking that in if we apply to M1 then we get minus of GMR 2 by 2 and into
so the only
input.
principle that you have to be careful, you have to be thinking about is whether the system comes out to be in negative feedback or not. Okay. So here you see plus and minus are all explicitly mentioned here, right? And you
Yes,
know that minus has to be connected to the V out terminal, isn't it? You
yes,
know that,
yes,
but
yes,
you do not know in this case, right? In this
right.
case, you do not know. In this particular example, you do not know. So tell me, what do you mean when you say that this is minus, this is plus, and you connected the minus to the V out terminal? What do you mean when you do
Inverting
this?
feedback, sorry, negative feedback,
Negative feedback. And how is that negative feedback?
because the output tends to become stable after connecting it. It
Well, that is
automatically
one
goes
way
to
to
the
understand it, but the more
the input. If
general,
we apply the input, the output will become inverted to what we get.
yeah. So this is basically for any system. If you want to check whether it is in negative feedback or not, if the loop is in negative feedback or not, you simply have to break the loop somewhere. Okay, okay,
Yes, yes.
and then you have to apply an input in one part of the
We
loop.
test.
In one side of the broken loop, you have to apply a test voltage V test. Okay, and you have to check what is coming back in the other side of the loop. Okay, other side of the broken loop, and you have to
Okay.
compare the signs. If let's say this was increasing, if this V test is increasing here, the return voltage that is coming here, it has to decrease. If that is happening, then you can say that this is a negative feedback loop. Okay.
Okay, sir. So in this case, we can take the output either from the drain of M1 or from the drain of M2, right? So
Yeah.
which one do we consider for this output?
Yeah, you say na.
V out.
You tell me what should you do?
Uh, I'm not sure about it.
Okay. So first thing, you see, why cannot you take the out? So what is the problem if you take the output from here and here?
They'll be
Clearly you
inverted
can
of
see
each
that these
other.
two are not same, right? These two terminals are not same. They are not symmetric,
Right,
right?
right.
So what is changing from between these two? What is the difference between these two terminals?
Uh,
We want to realize an op amp, right?
right.
Voltage control current, not an op amp but an OTA, a voltage control current source. We want to realize. And what is the property of of a voltage control current source? We want to realize a VCCS, right? And what is VCCS? Symbol wise, you have a voltage between
Transconductor.
these two terminals, and you have a current here, right? So this is, let's say, VI, and this is GM times VI. This is what we want to realize, correct?
Right,
Right now,
right.
correct. Let's say this is grounded, correct. Now tell me, now this is the output. This is the output, and this is the input. So let's not worry about the input. We are more concerned about which side should be the output, right? So what do
Yes.
you think? Which side should be the output? What is it? What is the first difference that you can see between these two terminals? What is making these two terminals different? Tell me. What is making these two terminals different? What is the one change that I can do in between these two branches to make sure that these two are symmetric? Right now they are not symmetric, right?
Right. So
So
M3 and M4 they are not same.
yeah, right. So what is different in between these two?
M3 is a diode connected
Correct.
load,
There is a
and
diode connected here, right?
yeah,
There is no diode connection
old,
here, right?
no,
So
right.
what is going to happen because of this diode connection at this terminal, which is not going to happen here?
M3 at the drain of M3 will have VDD minus VSG3.
Correct? Yes. True, true. That is one. That is one point. So I am more concerned about. Yeah. So you are right. That is one thing. Other thing. Can you say what happens uh, to the output resistance at this point, and what is the difference between the output resistance at between these two points?
Sir, at M3 the output resistance will be 1 over GM3, and at M4 it will be 1 over GDS4, that is in
Correct. Correct.
saturation.
I mean yes. Right. So clearly the output resistance at M3 will be much smaller compared to the output resistance at M4. Right.
Yes,
Right now.
right.
And you want to use this as a voltage controlled current source, right?
So
As
we'll
this.
take at M4. We'll take at M4
Yeah, because
transconduct. Output resistance should be high of a
yes,
current
yes,
source.
yes. So output is sorted, right? So you have to take the output at this point. Now tell me, in between M1 and M2, which should act as plus and which should act as minus inputs?
Mm, just a sec. Uh,
Focus on this. Tell me, which should act as plus and which should act as minus?
Sir, M1, if we apply, then the output will not be inverted to the input.
Correct,
Yes.
correct. So
So M1 would be the this positive input.
yes, M1 will be positive and M2 will be negative, right?
Yes.
You are right. That is what it is indeed.
Okay.
So is that understood now?
Yes, sir. Thank you.
Fine. Anything else?
Sir, just told one of the guy Gulshan that node VX should not be VCM.
Which node? This node?
Yes, sir. Can I share my screen for a minute?
Yeah, yeah, you can definitely share. Yes. Let me stop sharing. Yeah, you share.
Sir, is my screen visible?
No, not now. I cannot see your screen. Can someone else also? Can someone else see his screen?
No, sir, no.
No.
Okay, so let me check whether you have got the permission to share or not. Okay, 1 second. Yeah, you have the permission to share. You share. You can share. Yeah, go on. Please share.
Sir, it's taking a minute. You can continue. I will share it later on.
Okay. So
Sir, in assignment,
yeah,
Hello.
yeah,
Just one doubt. So this so the quiescent conditions are always Nagendra sir always says the quiescent condition. Is it this? What it means is that the same current I naught by two should flow to both the branches, right? The
yes,
differential pair.
yes.
This is this the case for all devices? Always should I naught by two flow through
Yes, that has to happen
always.
because these two are current mirrors, right?
Yeah, it's suppose that there's no current mirror. Instead, there's a R1 and R2, two different resistors.
Here at this point.
Yeah, instead of the two load transistors,
Hmm.
M3 and N4, two
Hmm.
resistors R1 and R2.
Okay.
So my question is, does it always have to be I naught by 2, that is the same current should flow through both the branches, or
No, if the
is,
resistors are different here, then the same
yeah,
current cannot flow.
same current one, provided GDS is not equal to 0, right?
Yes, provided GDS is not equal to 0. If
Equal to 0.
GDS is equal to 0 here, okay, then
Hmm.
yes, then same current will flow between both of these.
Okay, okay. So in this scenario, it is absolutely it's a sure fact that I naught by 2 will flow through both the transistors because of the current barrel, right?
Yes, yes.
Okay, okay, okay.
Sir, in ninth question, sir,
Okay, what is the ninth question?
they asked to find out the unity gain frequency, sir.
Okay.
So it means we have to find it in differential mode or common mode gain
No,
mode,
no,
sir.
for differential mode they are asking.
So for that C
I mean,
naught and
what?
R naught, sir.
Here, one second, one second. So there is no point in common mode differential mode here. I mean, they have already mentioned that this is for figure 1b. So why are you asking this question, common mode differential mode?
Uh,
They've already said that this is the figure that they are concerned about. This is the
yes,
figure
sir.
that they are concerned about, right?
Yes, sir.
So what is the meaning of common or differential mode here? There is no meaning of common or differential mode here. I mean, there is only one input here.
Yes, sir.
When is the when can you talk about common or differential mode? When you have two inputs, right?
Yes, sir. Two
Here
inputs.
here there is only one input,
Yes, sir.
so there is no common or differential mode. So just one input, and you have to find out this output. You have to find out what is the this thing loop gain here. Okay, so let's move on. I have to cover some things. Okay, so this question I already discussed in the one of the previous weeks. Okay, so I just want to do some more things here. Fine. So this is fine. This is easier to first in the first part of this question you have to find out what is the V naught. Sorry. First you so this is a condition. You have been given certain parameters for this particular transistors. Okay, and you have to find out what is the minimum possible value of this V naught. Minimum possible value of this V naught. Okay. So how will you find out minimum value of V naught here? This current I naught is given. Okay, so how will you find out V naught, minimum value of V naught? Come on guys, so this is like I have been talking about this for a very long time now, so this should be on your fingertips now.
VDS must
So
be
we can
greater
find
than
the
VDS
gate
minus,
voltage,
You have to find the gate voltage here. Okay, fine, this is the gate voltage.
and VDS
and
must be
then
greater than VG.
Yes,
Yes.
cool, so this is easy, right? This is easy, fine. Now how will you find out the minimum voltage V naught here?
Ensuring M2 is also in saturation, at the same time ensuring M4 is also in saturation,
Fine, so
depending on M2 also.
yes, right. So again, so tell now what will you do? So let me give you the numbers. When you start calculating I naught here, this I naught is equal to 0.5 milliamps. Okay, so you will see that the VGS required for I naught is equal to 0.5 milliamps is actually equal to 2 volts. Okay, fine, and VTH is equal to 1 volt. So this is easy to find out and you can do it. Now tell me what should be the voltage here? This current is zero
Volt,
point 0.5 milliamps. VGS for current of 0.5 milliamps is equal to 2 volts. VTH is 1
volt,
volt. What is the voltage here?
2 volt, right? 2 volt.
2 volts. Fine. What is the voltage here?
2 volts,
2 volts. What should be the voltage here?
4, I think.
4 volts. Why? Why do you say you think? I mean, this is so. This is there's nothing to think here, isn't it?
Yes,
Be confident. What is the voltage here?
Four only, sir.
Yeah, cool. Yeah, so now tell me, what is the minimum voltage V naught here? What can be the minimum voltage V naught here? When can V naught be
It's a
minimum?
2 volt.
Before jumping, please wait. So what? When can V naught be the minimum value? When can V naught achieve its minimum value? So one of you actually pointed out, right? When can V naught be the minimum?
Saturation.
When M2 is at the edge of the saturation.
1 volt, sir. 1 volt is the answer.
Yeah, when M2 is at the edge of saturation and M4 is also at the edge of saturation, right?
Yes, sir, yes, sir. Both of them.
Both of these have to be. So what should be the voltage here when M2 is at the edge of saturation?
VGS minus
1
VT.
volt.
1 volt. Fine.
Should be-
And
It's 2 volt.
now tell me what should be the voltage here when M4 is at
So
the
2,
edge of saturation?
2 volt. 3 minus 1, right? 4 minus 1.
Is it 2 volt? Is V naught equal to 2 volt?
1.
Yes, the gate source is 3 volt, right?
Right.
GS. So
Yes.
3
minus
minus
1 is
1 threshold below.
Yeah, correct. 3 minus
So it
1.
was 3,
This should be 3, right?
3 volt. Yes, sir. It's a 3 volt. Gate should be 1 threshold below it.
Right. Correct. Gate should be 1 threshold below. Or sorry, gate should be 1 threshold above, right? The drain voltage,
Yes.
right? So the minimum voltage at this point is what? 3 volt, correct? If you go
Yes, sir.
if you go lower than this, then M4 will first go out of saturation, okay? And after that M2 will go out of saturation. Always remember that in a cascode connection, the most critical is this transistor M4, which is directly at the output, okay? That transistor is most susceptible to going out of saturation when the output decreases, okay?
Sir, one question. Sir, for M3 the VGS is 2 volt, but in M4 the VGS is 3.
Yeah. So okay, so I appreciate your concern. So what? That's a good doubt. So see here, I have assumed that there is some output resistance, okay? If there is no output resistance, then crazy things will happen here. You assume that there is some output resistance. You assume some channel length modulation here, okay? Only then can the voltages be consistent. Otherwise, you will have problems. That's a good question. Yes. If you assume some output resistance, then this can hold, right? Because then the current will also be dependent upon VDS, not only dependent on VGS, right?
Yes, sir. Yes.
I mean, your concern was this, na, that VGS here is only 2 volts, but VGS here is 3 volts. So how can the current be here also? VGS is equal to 2 volts here, but VGS is equal to 3 volts. So how can the current be equal? That was your concern, right?
Yes.
Yeah. So for that only I am saying that that can only happen when the current is not dependent upon VDS. But I assume that there is some output resistance here. In that case, current will also be dependent upon VDS. Okay. Is that fine?
yeah.
Yeah. Fine. So let's remove this. Yeah. So what I was saying, I was saying that
Sir, in case of non dependent, so this is gamma into VGS. So
eh,
in small signal,
yeah, small signal mode. Are you talking about body effect?
no, that how depending on VDS you are telling. So how I'm not getting it, sir.
No, I am not understanding what you are asking. Are you talking
That
about body
depends.
effect?
No. That you were talking. You were telling that it's dependent on VDS also. That I'm not getting.
Okay. So if you assume channel length modulation, what is the equation of current? I naught is equal to what?
Okay. 1 plus lambda VDS. Okay.
Yeah, that is
Got
what
it.
I am saying.
Oh,
That clear, right? Is that is clear?
yes, clear.
Fine. So I was saying that always remember that in a cascode connection, sorry, that in a cascode connection, if V naught starts, if this is a cascode connection, right? This is a cascode connection here, output. Fine. So if the output of this cascode starts to go down, then what will happen? The most susceptible to going out of saturation, the first transistor that will go out of saturation will be M4. Okay, always remember that. That is always the case. It is M4 which first goes out of saturation. I mean, for properly biased cascodes. That is the general thing. This transistor, the cascode transistor, will be the first one to go out of saturation. Only and only after that M2 goes out of saturation. That is generally the case. Okay, and that is in general how it is biased also. Okay, so here this transistor, this is the minimum is 1 volt. The minimum of V out is 3 volts. So if V out goes below this, M4 will go out of saturation first, and after that this one will go out of saturation. Okay, is that clear? Is that clear?
Yes, sir. Yeah.
Fine. So fine, this is clean. uh, hmm. Fine, now just a small changes. So this was about the range here. Okay, what is the minimum and maximum thing? So let's clean this up, and let's do something else. So now assume that there is a capacitor attached to the source of M4. So at this source M4 I have attached a capacitor here, C. Okay, now sketch the incremental output impedance magnitude as you increase the frequency from DC to infinite. Assume that the transistors are in saturation. Now tell me, what is the impedance looking out when this capacitor was not here? What is the looking what is the R out here?
So GM4 RDS 4 into RDS2, right? Approximately.
What is R out?
GM4
GM4
RDS4 into RDS2.
RO4 into RO2, right? Approximately, correct?
Approximately.
Yeah, this is right, correct. So now when you attach a capacitor here, what should happen?
So it will go parallel with RO2.
True. I'm asking, first tell me what will happen qualitatively, then we'll get into
If
maths.
we increase the frequency, then the net impedance will decrease, right? RO2 parallel
Yeah,
C.
so first at DC, the situation is still the same, right?
Yes, sir.
This at DC, so at DC, what is R out? Again the same, GM4 times RO4 times RO2, right? Now at very high frequencies, we'll get into the exact how much high, but let's say at very high frequencies, what should be the output resistance here?
RO4.
Right, exactly. So it should be only RO4, correct? Right now. So the if you sketch the output resistance versus frequency, what should it look like? I mean, at DC, this is R out, okay, magnitude of R out, and then basically dB in dB, and this is a frequency log scale. So how should this plot look like? This is at 0 DC. What should it be? Should be log 20 GM4 RO4 RO2, right? Right now.
Yes, sir.
Yeah. Now at very high frequencies, what is the value of this? This is basically, let's say, this is at very high frequencies, this is log 20 Sorry,
R04.
sorry, this is not log 10, this is log 10, 20 times log 10. Okay,
Uh,
right. And this is RO4, right? This is at very high frequencies, right? So somewhere it should start decreasing, and then after some frequency this will become RO4, right? So clearly you have a pole here, isn't it? And this is a 0, right? Right?
yes, sir.
Now tell me, what is the pole and zero frequencies here? I think I discussed a question like this earlier also. So tell me, I gave you some intuition to how to find out pole and zero directly looking at this. Tell me, how will you find out? How will you say, how can you qualitatively say what is the pole and zero at this and for this particular picture?
So for zero, the V out would be like zero.
No,
So the
no,
current
no, no,
will
no, 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 no. 1 second, 1 second, 1 second. We are talking about R out, okay?
R out.
Yeah, yeah. We have this picture is R out for R out, right? This picture
Acha.
is basically R out, right?
Pole and zero of R out.
Yeah.
Yes, sir. Yes, sir.
So tell me, what will be the situation? So what should be zero at zero frequencies? Come on.
So I didn't get your question. What should be zero at zero frequencies? Like,
No,
what
no.
does it mean?
What should be the zero frequency?
Acha, the frequency of zero. Acha.
Yeah.
So I think it should be RO2 into C, right? 1 by RO2 into C, right?
Yes. Exactly. It should be that only. It should be 1 over RO2 into C. And what should be the pole frequencies?
So RO2 parallel RO4 into
Yes.
C.
Yes. It should be 1 over RO2 parallel RO4 times C. Yes. Indeed. So how did you find it out?
So the explanation is not quite good. Like, what I am saying is, I'm doing is like this. The current would be like for this 0 1, the current will flow in this loop only. It will not come out. So,
That is the explanation actually. That is a good explanation. That is an intuitive explanation.
but sir, there we're considering V out, right? Like, not R out. But here we are drawing this graph for R out.
Okay. So how do you calculate R out anyway? So you do this, right? To find out what is the
Yes,
current.
yes. Now I
Yeah.
get it.
So that is a good explanation. That is the explanation which I was looking for. Yes. That is it. Yes. So that is what. So you can clearly see, right? If you put a capacitor here, you cannot
Hmm.
guarantee very high impedances at very high frequencies, right? The impedance starts to decrease. Correct.
Yes, sir.
So that is why this capacitor here is of concern. So if it is a cascode, you always require a very high impedance, right? At the output, you require out to be very high, always, irrespective of frequency. But because of this capacitor here, you
Different
cannot
frequency.
guarantee it anymore at high frequencies. So this capacitor is actually of concern to designers. When it comes to design, this capacitor is something which you have to take into care. Okay.
Okay, sir.
Yeah. Fine. So yeah,
Sir, one doubt, sir.
yeah.
Sir, if suppose RDS1 equals to RDS2, sir.
RDS1 equal to RDS2.
Sorry, sir. RDS4 equals to RDS2.
RO4 equals RO2. Yes.
Then pole will be like 2 by pole frequency will be greater than zero frequency, no, sir.
1 second. I didn't get your question.
Sir, here pole equals to 1 by RDS4 parallel to R02.
Yeah.
If suppose they are equal, sir, then pole will be like 2 by R01 by C. I'm correct, sir?
Oh yeah, yeah, right, right, right. Okay, one second. Let's look into it. Let's look into it. One second. Okay. Hmm. So when what is the pole frequency here? Let's do this. GM4 times R4 divided by Okay, so one second. This is actually not correct. Plus RO. Yeah. So what is the whole expression for this? What is the whole expression for R out?
RDS2.
Yeah. So in terms of RO2 and RO4, tell me.
One minute.
It's RO4 plus RO2, right? Is this right? Hello.
Yes, sir.
Is this right?
Yes, sir.
Correct. So the whole expression here will be plus RO4 plus RO2 divided by 1 plus SCRO2. Correct. So let's see. You can clearly see that RO. So yeah, so pole location is actually wrong here. Looks like this is R out. Okay. Hmm. So it is actually equal to GM4 RO4 into RO2 divided by 1 plus SCRO2 plus RO2 divided by 1 plus SCRO2 plus RO4. So it will be what? GM4 RO4 plus 1 into RO2 divided by 1 plus SCRO2 plus RO4, and then this 2 will go, so GM4 RO4 plus 1 RO2 plus RO4 plus SCRO2 RO4 1 plus SCRO2. Yeah, so I made a mistake. So pole location is actually RO2, SCRO2. So this is not 0, this is the pole location. This is the pole is 1 over RO2 into C. Okay, and this is actually 0, 1 over RO2 parallel RO4 into C. Okay,
Yes, sir.
what is
Sir,
the
here
question?
from the equation we can derive that pole no, zero no, sir, from our root equation also.
Yeah, yeah, you can derive, right? So that is what I have done here. This is actually what I have done here. So it's not actually this also. This is something different. The zero location is something different. So it is actually equal to what? Uh, so 0 is equal to C. So here it is actually, the numerator is 1 plus SC RO2 RO4 divided by GM4 RO4 plus 1 into RO2 plus RO4. Yes, this is the numerator. So 0 is what? GM4 times RO4 plus 1 RO2 plus RO4 divided by C into RO2 RO4. Okay, this is that this thing. This is the zero frequency. So this guy should dominate here in this case. So I was wrong actually. That was a calculation mistake, and the so that was a calculation mistake which I did. The zero location is this. The first term will dominate here. Okay, first term will dominate. So basically it can be approximately equal to GM4 times RO4 plus 1 divided by C times RO4. Okay, and you can simplify it further to GM4 divided by C into plus what, 1 over RO4 into C. So this is actually equal to GM4 by C plus RO4, sorry, 1 over RO4 into C, 1 over RO4 into C. Yeah, so this is what it is. Hello?
Yes, sir.
Yeah. So is my screen visible? Hello?
Yes, sir.
Yes, sir. Yes, sir.
I
Yes,
guess
sir.
it is stuck. Is the screen changing? I am changing my screen.
Yes, sir. It is changing.
Okay, now it is changing. Yes. Fine. So I made a calculation mistake there. Okay. So anyway, so you can find the R out directly. I mean, you can find the R out using the expression, and then you can see what is happening. So, but qualitatively you can clearly understand, right? But initially the output impedance is very high, and at very high frequencies the output impedance decreases, right? So that you can qualitatively find out, and so you can get the approximate behavior qualitatively, and then to calculate the exact value of poles and zeros, you will have to get into maths. Okay, so the intuitive explanation was wrong. Okay, so that was not correct earlier, which I was saying, that was not correct. Fine. Fine, right?
Yes, sir.
Yeah. Cool. So let's move on to another problem, which is, yeah, this is interesting. So what is this? Can you tell me what is this? I mean, have you
So
seen?
one thing, these
Yeah.
questions are they from Bazad Razavi
No, this is
or
this
from
is
someone else?
this is from other place.
Okay, okay. I know questions Bazad Razavi is fine, right?
Yeah, 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 yeah. Yes, that
Yeah,
is fine.
okay.
Yes. Yeah. So, but anyway, so do you identify this? So, have you seen it somewhere else? This kind of connection.
Is it white swing?
Yes, this is a wide swing. So, what is the other name for this wide swing? This is telescopic cascode, right?
Telescope.
Hello.
Yes, it's telescopic.
Yeah, this is telescopic cascode, right? So let's see what is happening. So earlier you remember, right, that when we had this condition, we had this, uh, not this one. When we had this, the minimum value of V out for a current of 0.5 milliamps, this was equal to 3 volts, right? In this case, VO minimum was what? 3 volts, correct? We found out, right, that VO minimum was 3 volts here.
Yes.
Now let's see, this is exactly the same thing. This is exactly the same thing, except that now we have this telescopic cascode here. Okay, all the other parameters are same. Okay, again it is 0.5 milliamps, and VGS for 0.5 milliamps is equal to again 2 volts. Okay, and VTH is again here 1 volt. Fine. So tell me, what is the minimum? Okay, so let's find out one by one, everything one by one. So what will be this voltage? Gate of M2, this here. What will be the voltage here? Hello.
Could you
Solve
explain
the
how is it
equation.
working actually?
What?
Solve the equation, sir. ID equals to half mu n C by x
Yeah, I
W by
told now.
L.
I told now. What is VGS for current of zero point 0.5 milliamps? It should be 2 volts. So tell me what should be the voltage here? How much current is flowing? I naught is equal to zero point 0.5 milliamps is
2
flowing
volts,
inside
sir.
here. Huh?
2 volts.
Yes. So this is 2 volts. So what should be this voltage? This voltage.
2 volts.
Fine.
2 volts.
This should also be 2 volts. Fine. Now, now I want this. I want. So what is the purpose of using a telescopic cascode? So you have done the class. So what is the purpose of using a telescopic cascode?
To increase the gain.
Yeah. No, I don't think so.
To minimize the overhead voltage that VO.
Right. So basically, VO can go even lower with this telescopic cascode, right? Right now.
Yes, yeah,
Correct.
yes, yes.
So this is a wide swing. So VO swing increases. So tell me, uh, where should I bias? So what should I? Now this voltage is dependent upon what? This voltage is now not controlled by these two voltages, right? 2 volts, 2 volts. This is not in its control. So who sets these two voltages? Or even before that, who sets this voltage here? This voltage here. What should be the value here? I mean, what sets the voltage here at the drain of M2?
VDD.
Clearly everything is set by VDD, but so look at this transistor M4, right? This M4 requires certain gate to source voltage, right? Uh, to ensure that current of zero point 0.5 milliamps flow through it. Yes, this transistor M4, there should be some voltage between gate and source, right?
Yes.
Only then 0.5 milliamps can flow through it. So tell me, uh, okay, so you know that already, that this voltage VGS has to be equal to 2 volts to support this zero point 0.5 milliamps current. So the gate VG, let's call this voltage as some Vx, okay, not Vx but Vg. Let's call this as some Vs, okay. So clearly Vg minus Vs has to be equal to 2 volts, right? For 0.5 milliamps to flow through M4, isn't it?
Yes.
Correct. So tell me, so what sets the value of Vs? So what is Vs here? Vs actually is equal to what? Vg minus 2 volts, right? Vs is equal to Vg minus 2 volts, right? So what I'm asking is, if you want to ensure that V0 can achieve a minimum value, what should be the value of Vg here? How can you ensure that V0 goes even lower than earlier? So there was this condition, right? There was this condition in which you saw that V out was going to a minimum of 3 volts. Okay, you saw that V out was minimum of 3 volts only. Here you want to go even lower than that. So what is the one thing that you can change? What is the minimum voltage V0 can attain here? Who governs that?
VG, sir.
VG, and only is it only governed by VG?
And VS3.
VS3.
Yes,
Correct.
TV.
So if you want to reduce VO, you have to reduce VS, right? Isn't it? Am I right? Hello.
Sir, VDS equals to VGS minus VT, no, sir?
That is for the edge, that is for the transistor to remain at the edge of saturation. Yes.
Sir, S will be constant, no, sir? Then VD equals to VG minus VT, so
Yes. Yes. Yes.
it
VT
will be
actually.
independent of S, no, sir?
Yeah. 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 So no. Okay. Okay. Oh, I understand your concern. Yeah. Yeah. True. But you do not know what is VG at this point, right? You do not know what is VG at this point. Correct.
Yes, sir.
So clearly, okay. So let's talk in that manner only. So if you want to make sure that V naught achieves its minimum value, then if V naught goes low, M1 starts to go out of saturation, and also M3 also starts to go out of saturation, right?
Yes, sir.
So if you do not want M1 to go out of saturation, what is your minimum value that you need here? 1 volts, right?
One volt.
Correct.
Yes, sir.
Now if it is 1 volt, okay, this 1 volt also has to be we have to have that 1 volt here also at M2 drain also, right?
Yes, sir.
Because this and this are same, M1 and M2 are same, correct?
Yes, sir.
So this also can go a minimum of 1 volt only, right? Now as you clearly pointed out, this M for M3 to remain in saturation, this gate VG has to be 1 overdrive above V naught, right?
Yes, sir.
Correct. So
Yes, sir.
if you want to reduce the minimum, if you want to reduce V naught, you have to reduce VG, right?
Yes, sir.
So if you have to reduce VG, what is the minimum value that you can have at VG? Who will govern that? If VG starts to go down, if this voltage starts to go down, clearly this VS will also start to go down, right?
Yeah. Yes, sir.
Because 0.5 milliamps has to flow through this transistor, correct? Correct.
Yes, sir.
Right.
Yes, sir.
So now you already saw that the minimum value of this Vs is 1 volt. So what is the minimum value Vg can take? Vs is
3
given
volt.
here. Vs is 1
3
volt. Yeah.
3 volt.
Yes. It is 3 volts. And it came out because Vg minus Vs has to be equal to 2 volts, right? So Vs is actually
Yes, sir.
equal to 1 volt. So Vg has to be equal to 1 plus 2, 3 volts. Correct? Now if Vg is equal to 3 volt, then V naught can achieve its minimum value, right? When all the transistors
Yes, sir.
remain in saturation. So now tell me, Vg is equal to 3 volts, and so how low can V naught go? What is the minimum value of V naught?
Yes.
2 volt.
1 volt.
What?
Again, what? Why is this confusion? Why should it be should it be 1 volt? This V naught can go only one overdrive, one threshold voltage lower than Vg, right? It should be 2 volts, right?
Yes, sir.
Correct now. So Vg minus Vt, Vgs minus Vth has to be less than or equal to Vds, right? And here Vg minus this Vgs can be written Vg minus Vs minus Vth has to be less than Vd minus Vs. Vs and Vs go, so Vg minus Vth has to be less than equal to Vd. So the drain voltage can be as low as one threshold. Can only go one threshold below Vg, the gate voltage. After that, if it goes further lower than that, then the transistor goes out of saturation. So V naught minimum is equal to 2 volts in this case. So clearly, in the earlier case, you remember, right? Earlier case minimum voltage that this could take was 3 volts, but here the minimum voltage is 2 volt, right? Correct.
Yes, sir.
Yeah. So okay, now tell me something. This analysis we did, but there was a catch here. I mean, there's a constraint here. This constraint, can anyone point out? I mean, this cascode thing which we did here. Let's remove junks from here. Fine. So this was 2 volts. This was 2 volts. This we biased at how much? 3 volts. Fine. This was 1 volt. Okay. This was 1 volt. Fine. So we ensured that M3 and M1 are in saturation, right? When we did this, correct? So in the condition of when
Yes.
VO goes to minimum of 2 volts, then M3 and M1 are in saturation. Now let's talk about M2, M4. Let's talk about them also. So see, for M4 to remain in saturation, for this transistor to remain in saturation, the, this voltage, okay, this the drain to source voltage, okay, basically the drain of M4, which is, let's call VD of M4, has to be what? Greater than VG of M4 minus VTH, correct? That has to happen, otherwise this transistor will go away, right? Hello?
Yes, sir.
Yeah. Here you can see that clearly that is the case. Clearly this condition is being fulfilled here. This M4 is indeed in saturation here, right? In this case, it is already guaranteed. But let's do some maths here. So M4, to remain in saturation, you require this condition, correct? And what is VG of M4? VG of M4 was found out by putting a constraint here, right? This was 1 volt. So VG of M4 is dependent upon VD of M2, right? So what is the maximum value that okay, so what is the constraint on VD of M2? Has to be greater than or equal to VG of M2 minus VTH, correct? So clearly VD of M4 has to be greater than or equal to, if you put these constraints here, so this will get plus,
1 volt, sir.
no, that is fine. I am finding a constraint here. VG of M2 should be less than or equal to VD of M2 minus plus VTH, correct? Sorry. Yeah, so this is for this transistor M4, okay? This is for this transistor M2. This is for M4 to be to remain in saturation, and this is for M2 to remain in saturation, okay? Now what is the minimum value, what is the constraint of VG of M4? This VG of M4 minus VS or VD of M2, VG of M4 minus VD of M2, this has to be equal to some overdrive, right? This has to be equal to some voltage in order to make sure that 0.5 milliamps is flowing through it, correct? It has to be equal to what? This has to be equal to some let's call it some V, some delta V, okay, which is a constant value. So VG of M4 is equal to some delta V time some delta V plus VD of M2. So you may be wondering what I'm doing here. So what I'm doing here is I'm trying to find out a constraint here. You cannot always do this business here. I mean, there is some design constraint involved while using this kind of telescopic cascode. Okay, there is some design constraint involved here. You cannot always guarantee that you will get you will get this VO minimum is equal to 2 volts. I mean, you cannot always guarantee that all the transistors remain in saturation in this particular when you do this telescopic cascode business. There are some constraints here, so that is what I'm trying to find out here. Okay, so this VGM4 I'm putting here. So VD of M4 has to be greater than equal to this I am putting here. Okay, what is VGM4? This is delta V plus VD of M2 minus VTH. Okay, and this VD of M2 I am using from here. Putting here. So this is VD of M4 is greater than equal to delta V plus VD of M2 has to be greater than VG of M2 minus VTH, and then again this minus VTH. Fine. So VD of M4 has to be greater than delta V plus VG of M2 minus V2 VTH. And what is VG of M2? This is again, this VG of M2 again is equal to the same delta V, right? VG of this is again the same delta V. What was delta V? Delta V was the amount of delta V was basically VGS was equal to delta V for I naught to flow. Okay, so VG of M2 is again equal to delta V. So VD of M4 has to be greater than 2 delta V minus 2 VTH. Okay. Hello? Hello? Hello?
Yes.
Yes, sir.
Yeah. So are you with me or not? I mean, is this complicated for you?
No, sir.
Okay, fine. So what I'm saying here is that okay, so you are getting this constraint here. Fine, you're getting this constraint here. Okay. So what I'm saying is that okay, so let's not get into maths. I mean, this will confuse you. I'm not seeing any response, any activity from you. So maybe this is too much. This is too much for you. So you see, I will explain what I was trying to do qualitatively. So what you see that in this case you are tying this voltage and this voltage together, right? You are tying the drain of this transistor M4 and the gate of M2 together, isn't it? You're doing this.
Sir.
Fine. Now while doing so, you can clearly see that this M2 is an NMOS, right? M4 is also an NMOS, correct? So if the M4 has to remain in saturation, what is the ideal situation of M4 to remain in saturation? This drain has to be as high as possible, right? If drain goes very high, then M4 remains in saturation, correct? Right?
Yes.
Correct. Now if but this drain of M4 is not independent. This drain of M4 is actually tied to the gate of M2, correct? So the drain of M4 is actually fixed now because it is tied to the gate of M2. It is fixed because 0.5 milliamps has to flow through M2, correct? That is why this will become fixed. This is also fixed, correct? Fine. Now what will
Yes.
happen is that this but this M4 transistor, okay, this M4 transistor has to remain in saturation. So what is the ideal thing to do? If you can make sure that this goes down, this gate is very low compared to this gate goes down, then you can ensure that this transistor M4 always remain in saturation, right? And what is the ideal thing to when can this transistor M4 go out of saturation? Only when the gate goes above one threshold above this, right?
Yeah.
Correct?
Yes. Yes.
Yeah. So if you want to make sure that M4 is always in saturation, then this if you reduce the gate voltage here, then M4 will always remain in saturation, right? Correct now.
Yes. Yeah.
Yeah. But when you start decreasing the gate of M4, what will happen? The source will also source will also start to go down. Correct? And what will happen is that you will see that M2 starts going out of saturation. So earlier that was not the case. When these two were diode connected individually, you can clearly see that these two transistors can never go out of saturation, right? M4 and M2 can never go out of saturation. But now that is not the case. And it when you start designing, you will see that this is a problem with this kind of uh, cascodes. Okay, telescopic cascode. This is a problem in design, that you will have to have this basically this whatever I was saying and whatever maths I was trying to do here, this basically translates into a certain constraint on the threshold values of the transistors. Okay, of these transistors. And if the threshold values do not satisfy those constraints, then you cannot design a telescopic cascode with those transistors. Okay, so maybe I will discuss this later. This is neither the time nor the place. Okay, so we will discuss this later
Sir,
maybe.
sir, we have to check for the saturation carefully in this case, sir, rather than previous one.
So previously you see that this was a diode connection, right? This M1 and M3 were diode connected. They can never go out of saturation. Correct?
Yes, sir.
But here that is not the case. That is not the case here. And the problem is that this will basically translate into some constraint on the threshold values of M2, M4 and the gate overdrive of all those transistors. Okay, and you will see that if that is not satisfied, then you cannot design a telescopic cascode. Okay, you will not be able to design a telescopic cascode. Forget about saturation, you will not be able to design it. Yeah, so basically some transistor will go out of saturation if that is not satisfied. So we'll talk about it later. So I thought that maybe I can cover this, but let's keep it for someday else. This is slightly complicated, so next tutorial I will start with this only. Fine, let's see. Okay, so this is for your benefit, these two questions you can try on yourself. mm, yeah, so hmm. So this is a simple cascode op amp, right? This is simple cascode op amp, right? Hello. Hello.
Yes, sir.
Yeah, yes, please speak up. I mean, I cannot hear you, then I don't know whether you are present or what. Fine, so you can find out the values here, right? You can find out the DC values if all the parameters are given here. Fine, and you also know what is the current I naught. Then you can find out all the DC voltages, isn't it? Vx, Vy, Vb0, everything you can find out. Correct? After that, yeah, here also. Now tell me what is the minimum value of this common mode voltage. So this is here, this is here. Okay, this is VCM, this is also VCM. So what is the minimum value of this common mode voltage VCM? How minimum can it go?
VGS1 plus VDSAT 0.
VGS1 plus VDSAT 0.
VDSAT 0.
VDSAT 0. VGS1 plus.
VDSAT 0.
Sure. Are you sure? So VCM minus VS has to be equal to what? Some VGS, right? VGS1. Correct? Right now. And this Vs has to be greater than equal to VD sat 0. Correct? So let's see, VCM minus VDSAT 0 has to be equal to VGS of M1. So VCM can go a minimum of VGS of M1 plus VDSAT 0. Fine. So you were right. Fine. This is good. So what is the maximum value that this can go? What is the maximum value VCM can go? What is the maximum value that VCM can go?
VD2 plus
Okay, no, no. Tell me. Okay, so
VS.
don't. Okay, so when I ask what is the maximum minimum, don't shoot the answers, please. Okay, tell the procedure. Okay, I do not require the answers. I only require the
Sir,
procedure.
M2 should be in saturation, sir.
When
That's the
VCM
condition.
starts to go up, which all transistors can go out of saturation?
M2, sir.
M2, and what about M4? Well, will M4 be affected?
Uh,
No, sir.
no, sir.
Yes, good. M4 cannot be affected because the gate is fixed, and it has to have a current flow of I naught by 2, right? So source is also fixed for M4, correct? So the only transistor that is going to be affected will be M2 and M1, right? So correct. So only an M2 and M1 can go out of saturation. Fine. So this is clear. Now tell me, what is the maximum that V out can go? Now how will you find out?
M0 should be in saturation.
Why? V out, I'm asking. V out, what is the maximum it can go?
Sorry, sir. M above M4, sir. M8.
Okay, so now is it visible?
Yes, sir. M8.
M8 should be in saturation, right?
Yes, sir.
And also M6 also should be in saturation, not only M8.
Yes, sir.
When you start moving V out, then this node will also move out, right?
Yes, sir.
So M6 and M8 both should be in saturation, correct? Fine. Now tell me, what is the minimum that V out can go?
M4 in saturation.
Good. So M4 is the only one which. Now, 1 second. And also also M2, right?
Yes, sir.
And also M0.
Yes, sir.
So all these trees would be in saturation when V out goes down. Every voltage will be moving in that scenario, in that situation.
Sir, here, sir, minimum V out can be 3 VD sat. No, sir. If assuming that VD sat equals to
Yeah, yeah, yeah,
all
yeah,
VD
yeah, yeah.
sats of
Yes,
same.
yes, yes. I mean,
Sir, here output swing will be like.
yeah, it will be skewed. It is limited by the minimum this thing. Yes.
Sir, in above, sir, above V out equals to VDD minus VD sat 6 minus VD sat 8.
Yeah, correct. But here it will be. So basically, this will be only two transistors here, right? But in the bottom we
Yes,
have three transistors. So clearly it is skewed. I mean, the top floor. I mean, let's say this is VDD, and let's say this is the maximum, and let's say this is minimum, and let's say this is the ground. So clearly this is larger compared to this. Okay, is that clear?
yes, sir.
Fine. Okay, moving on. Uh,
But,
yeah.
one doubt.
Yes.
In this scenario, if V out decreases, how does the drain of M6 also decrease? Is it because of GDS is not equal to 0? Current should be the same. Is that why?
1 second, 1 second. Which drain of M6 you are saying?
Yeah. If V out decreases,
Huh?
the drain of M6 should also decrease because of GDS not equal to 0, right?
Yeah, correct.
Okay,
So,
okay, okay. No, no, it's okay. That's it.
okay, fine, fine. Okay, so this is done. So that's all. I guess you will be able to solve the questions after this. Fine. So in the next class, I will watch that part. What was that question? One person asked me. There was a question, right? This someone asked me. Yeah. So someone asked me like connection V out to this thing. So which lecture is that? Where there is a V turb something like that. Someone was saying
Week 10,
week 10. Week 10. Which lecture exactly?
last third lecture.
Last lecture, right? Okay, I'll see that and I'll check it out what he was trying to say. Fine, and
And 9 and that last two.
last two lectures you are saying?
Last two lecture. Yeah, some conclusion is coming from the previous second lecture.
Okay, so week 10 last two lectures, right?
Yes.
Fine, I'll watch it. And okay, so this is fine. Yeah, so next class remind me, okay? I will start with this telescopic cascode. There is a constraint which comes out to be there is some constraint on the threshold value and the overdrive. Okay, only then you will be able to set. Oh, if you satisfy that, only then you will be able to design this telescopic cascode. Okay, next class I will start with that. That is an important constraint. That is a design constraint. Fine. So thank you
Sir,
for joining.
sir,
Yeah.
sir, can I now share my screen?
Okay. 1 second. Yeah. Go on.
Sir, is it visible?
Yes, it is visible. Yes.
Sir, in the common mode, you told that Gulshan that this point that this point should not be a VCM.
Which point
That
should
tail
not be
one,
VCM?
sir, the tail one, sir, where I naught is connected.
Okay. So that point should not be VCM. I said.
Yes, sir.
Okay.
Sir, but in this, sir proved actually in the lower part to the circuit that this should be VCM since
Hello.
the current that extra should be flowing will be VCM by R naught in the lower direction. If any R naught is also connected.
I do not get your point. I'm actually not able to hear you also. So what I was saying is that that in that case I said VCM. It was not able to equal to VCM because there was some finite output conductance. There was a finite resistance connected there at the base. Here it is at the source. Here there is only I naught connected. I naught is a perfect current source. So there is no resistance here, right? So in that in this case it will be VCM only. But in the case that I was discussing, there was a resistance connected parallel to I naught.
Sir,
Yeah. Hello. Hello.
sir, in this the so when I asked you the question about that point VCM, so I was going through the analysis and I said that the drain should follow the VCM, right? Even if there is a register connected. So actually, what he is trying to say is this is a common drain mode, right? So shouldn't it follow the small signal VCM, like the
No, no, that is
source
what
of
I was
this?
saying. Na, if there is a resistor connected, it will follow it, but it will not be exactly that. There will be some. It will not be exactly
Yes,
VCM.
exactly. There would be some mismatch. Like it would the gain would be less than one.
Yeah, right. So that is what I was saying. Na, the gain will be less than one. There will
So,
be
but
some
in
variation.
the
It will not be
question,
exactly VCM. There will be some
in
different. It will be different value.
so in the question that is given, like in the week 10, so when I'm calculating actually, when I'm calculating the exact procedure, so it is coming like very close to one, like
Yeah. So
because
that
R
is
naught is
fine.
given 1 meg.
Yeah, so then it is fine. Then it is fine. Then it is fine.
So the problem that I had is after that, like after I am like seeing that the current flowing through I naught through R naught is VCM by R naught, and it will be divided half, right, between these two transistors. Half will flow through M1 and half will flow through R2,
Yes, yes,
and then we have to calculate V out, right, through that. Like I naught by 2 is flowing through M2, and we have to calculate V out. So there I'm getting stuck. Like, how do I proceed from there?
so what I will suggest is, do this. Use principle of superposition, okay, and then find out what are the values and add them. And if that is, that will give you correct answer. Okay. I mean, simple. It is simple, right? Simple to do. Simple principle of superposition, right?
Yes, sir. Yes, sir. So the question I can do.
Attempt using that, and that will definitely give you the correct answer. If that is, and then you can basically debug from there what you were doing wrong in the previous analysis.
Uh,
Okay.
okay,
If there
sir.
is some other doubt, and we'll discuss it in the next tutorial. Okay. Okay.
Okay, sir.
Okay. So that's it. So let's call it for today. Thank you for joining. We'll meet again next
Thank you, sir.
Monday.
Thank you.